Okay, today we're going to talk about exponential functions and bank account interest. Okay, interest is something your bank account gives you for taking your money. Now, your bank holds your money and they give you some interest. Part of the reason they give you interest is probably you've heard your parents talk about that used to only cost this much, or your grandparents maybe talk about, remember when gas used to only cost a quarter per gallon, and things in life go up. So if you save $1,000 for 20 years, that $1,000 is actually worth less. You can buy less with it in 20 years. It's not worth less than $1,000, but $1,000 won't be worth as much in 20 years as it is today. So interest is something that is given to you on your money by a bank, or by the stock market might give interest for using your money. Okay, so there's two types of interest. There's simple interest, which you invest $20,000. Maybe when you were born, your grandparents, this would be great for everybody if your grandparents had been able to give you $20,000 to save to go to college. Let's say you get 3% interest. This is way more than any savings account is currently getting, but 3% simple interest. That means I get on my $20,000, 3%. I need to convert my percent to a decimal. I do that by moving the decimal 2 places to the left, and I get 0.03. My interest is then 20,000 times 0.03, which equals $600. So I get $600 every year, just for my money being in the bank. That sounds pretty good. So after the first year, I've got $20,600. So if I want to know how much total interest I get in 18 years, I was getting $600 per year. So that is just 600 times 18. I get $10,800 interest, leaving me with a total of, no, I need to add correctly. I just add my interest to my initial 20,000 and I get $30,800. That's not too bad. Okay. I've made $10,800. I'd take that. Now, I'm going to introduce you to something called compound interest. Compound interest means I'm going to get my 3% interest on all the money that's in my account. So if I've got $30,800, this simple interest, I got 3% on my initial 20,000 that I put in. Compound interest, which is what banks actually use, I will get 3% on all the money that's in my account. So the first year I have 20,000, I get 3%. That's 20,600. Here, my second year, I'd get another 600, so that's $21,200. Here, my second year, I get 20,600 times my 3%. So I'm just going to put that into a calculator. And I get $618 interest. So I'll add that to my 20,600. I get 20,218. I got an extra $18. That's not bad. I'll take that. If you want to go directly to it, so what I'm doing here is 20,600 times 0.03, and then I added 20,600, essentially times 1. What I can do here is 20,600 times 1.03. Okay, now the next time I've got to take 21,218. Well, what I can do with this is I can write an exponential equation with this 1.03, but instead of having to redo times 1.03 each time, I can do 1.03 to the x. Okay. Now, if I did it for year 2, I do times 1.03 to the second. And I want everybody to grab a calculator and actually do this. And that still gives me 21,218. If I want to know the 18th year, now I'm going to do 20,000 times 1.03, or my 1 plus my interest rate as a decimal to the 18th. This now gives me $34,048.70. So by using compound interest with even a pretty small interest rate, this is better than you'll get on a savings account, but hopefully you could get better than that if you used an investment account. We were able to gain an extra $3,000 just on interest off the other interest accumulated. If you made this for something like 40 years, we'd get a huge difference, significantly bigger difference. So over here at year 40 on simple interest, I'd have $44,000. Over here at year 40 on compound interest, I'd have $65,240.80. Pretty big difference there. Compound interest represents very large amounts of growth. So I also want to talk today a little bit about exponential functions, which compound interest is an exponential function. Hopefully at some point you've talked about exponential functions before. The difference here with an exponential function like 2 to the x versus a quadratic function, which we'll talk about next, y equals x squared, is exponential functions have this variable in the exponent. They follow this general form y equals ab to the x, where a, if there's no shifts or translations, like we've talked about shifts and translations up, down, left, right on our absolute value functions, if there aren't any of those, this is the y-intercept. In word problems, they'll talk about it being the initial value. Okay. The y-intercept could be moved by shifts, and this b represents our growth, or sometimes exponential decay factor. Oops, got to spell decay correctly. Growth or decay factor. Okay. Now, one like this, 2, is an exponential growth. Here we have a b value of 1/2. That's an exponential decay. This means we're halving each time. This means I'm doubling each time. So you're going to see things referring to the B value. For growth, B must be greater than 1. If we're dealing with decay, we're going to have values of B that are between 0 and 1. Notice I've never put a 1 in there because 1 to any power, 1 to the 1 millionth power, still equals 1. So then that just becomes A times 1. I've also not put in negatives for B because a negative, to say the 1/2 power, we just learned that the 1/2 power was like the square root, and say B was -2. When I get to 1/2, that's like square root of -2, and that's not a real number, okay? So exponential functions are going to be smooth, and they do require that B be a value greater than 0, okay? But not 1. 1 will not be exponential either. So I'm going to pop over to Desmos here for a second. Here I have resumed, or I have graphed the function in Desmos. And that function for me is y equals 5 times 2 to the x. Okay, I've got it right here. I'll show you how to enter this one. And this is what exponential growth looks like. It's going up. The function is increasing as I go left to right. I always go left to right, so this is an increasing function. That would be an exponential growth function. Below it, I'm going to put a decay function. So I'm just going to add another line in Desmos. And here, it pulled up the Desmos keyboard for me, which is kind of nice. It's down in the lower left-hand corner down here. You'll click on the little keyboard thing. And I can use my regular keyboard to type things, but it's helpful to have this Desmos keyboard for other things. And I use the asterisks for the times, or I can click on the times on my Desmos keyboard. I'm going to do 1/2. I'm going to put parentheses around 1/2. Notice when I just type that, I need to use the right arrow on the keyboard to get out of my denominator. And then I'm going to use this A to the B button. Click on that. Oops. And put to the X. Now notice this is going the other way. This here we've got here in green, our exponential decay function. This is a decreasing function. As I go left to right, it goes down. So I can identify my growth or decay based solely on this B value. This initial value here, the 5 on both of these, is my y-intercept. If I come to over here and I click on where it hits the y-axis, it'll give me a 0.05. That's a y-intercept. 0 is my x, 5 is my y-intercept. And so this is how I graph them in Desmos. I could take a look. If I'm not sure if it's growth or decay, I should initially look at the B value, see is it larger than 1 or is it between 0 and 1? And again, when I say B value, I am referring to the form y equals AB to the power of x.